Okay, so this is like my fourth time trying to film this video, so apologies if if I kind of sound like I'm losing it. Okay, acids and bases. So I'll go over like the very basic descriptions of each, like pretty fast. Acids are sour, corrosive, have a pH less than 7, um, and then they also conduct electricity, whereas bases are bitter, slippery, have a pH greater than 7, and then that's an H, not a 7. And then they also conduct electricity. Now, just to quickly explain why both acids and bases conduct electricity is that an acidic or basic solution is going to have some sort of ion in it. If it's acidic, it's probably going to have a greater concentration of hydrogen ions, and if it's basic, it's probably going to have a greater concentration of hydroxide ions. And because there is ions present in these solutions, they can conduct electricity. So electrons can pass through these solutions like pretty easily. Go over the three models of acids and bases. The first is Arrhenius, the second is Bronsted-Lowry, and then the third is Lewis. Now, these are kind of going in order of most specific to least specific. So, like a Lewis acid is going to have like the broadest definition, while the Arrhenius acid is going to have like the most specific definition. So, starting with Arrhenius, Arrhenius defines an acid as something that is going to be giving off protons into a solution, or something that is going to be increasing the concentration of protons in a solution. The Bronsted-Lowry model proposes that an acid is something that is donating a proton. And then the Lewis model is saying that an acid is um, being in a electron pair acceptor. And then for bases, Arrhenius says that a base is increasing the concentration of hydroxide ions. Bronsted-Lowry is saying that it is accepting a proton. And then Lewis is saying that it is donating an electron pair. Now, I'll do specific examples of Arrhenius and Bronsted-Lowry because those kind of have to do with more like specific concepts that we learned in class. However, Lewis, as you can see, like electron pair acceptor donating an electron pair doesn't really relate to anything that we did or we went over in class, so I'm not really going to be covering that. Okay, one of the more specific things that has to do with the Bronsted-Lowry model is conjugate acids and bases. So conjugate acids and bases have to do with what is gaining the electron, not the electron, the proton, and what is donating it. So, for example, if we have ammonia in H3 and that reacts with water in a solution, we are left with ammonia um, ammonium, and then hydroxide. So in this case, ammonia gained a proton from the water. So in this case, ammonia is a base, and then water is donating a proton. So in this case, water is an acid. And then we have our conjugate acids and bases on the product side. So ammonium is the conjugate acid, and then hydroxide is the conjugate base. Now, this also introduces us to the concept of amphoteric substances, which states that a substance can be an acid or a base. And one of the biggest examples of this is water. So water can either donate a proton or it can gain one. So if we take nitric acid, for example, which is HNO3, and then react that with water, we are left with um, nitrite, which is NO2, um, sorry, just nitrate, and then hydronium, which is H3O plus. So in this case, water acted as a base because it gained a proton from the nitric acid. So water was the base, nitric acid was the acid, and then the conjugate acids and bases are nitrate and hydronium. So in this case, hydronium is the conjugate acid because it is what gained the proton, and then nitrate is the conjugate base because it is what lost the proton. Moving on to strong versus weak acids and bases. And this mostly applies to the Arrhenius model of acids and bases because as you'll see, it has to do with something increasing the concentration of either hydrogen ions or hydroxide ions. So first we're going to start with acids. So for our acid example, we're going to be using let's do hydrochloric acid, so HCl. Um if you put HCl into water, then it is going to quickly ionize or disassociate. Both are two words that apply to the same phenomena or occurrence, whatever you want to call it. And the hydrogen ion and the chloride ion are going to separate. So we're going to be um you're going to be left with hydrogen ion and a chloride ion. And then this is an example of a strong acid. So it is going to completely ionize. Hydrochloric acid is going to completely ionize. All of the particles are going to completely separate into hydrogen ions and chloride ions. And then the same thing also applies to to bases. So if we take a strong base, for example, NaOH, sodium hydroxide, if we put this into water, it is also going to completely um ionize and form sodium ions and hydroxide ions. And if we create a visual representation of this, if we have a solution with a strong acid or base versus a solution that has a weak acid or base, um, in a strong solution, these particles are going to be completely separated. Um, the two atoms or like polyatomics that make up the acid or or base are going to be completely separated. However, in a solution that has a weak acid or base, only some of these particles are going to be completely separated. Some of them are still going to be like intact. So as you can see here, I'll circle them to make it a bit more clear. These ones are like still intact. Well, that one's not. Well, the rest are like ionized. So this also means that when we're writing the equation for a strong acid or a strong base, um, if we have substance Cb, we put that in water, it is going to completely ionize to particle C and particle B. However, if Cb were a weak acid or a base, Cb would some of Cb is going to ionize into that C and B. However, some of it is just going to stay as Cb. So when writing the equation for this, we're going to be using the double arrow signs because it's existing in both states. And then this will be more important when we get into Ka and Kb constants.